Next, let's look at the properties of relations, and we are going to define four main properties and here to classify relations. And the first property we are going to talk about is reflexiveness. So a relation R on set A is reflexive if for all x in A, x is related to itself through this relation R. Now, how do you spot this? When you look at the D graph, you have to have a loop at every vertex. And if you look at the 0-1 matrix, you have to have all ones at the main diagonal. If you have just a single zero, the relation is not reflexive. The next property is symmetry. A relation R on set A is symmetric if for all xy in set A, if x is related to y, that means the ordered pair xy is in relation R. That implies y is related to x. This means yx, the ordered pair, is in R. Okay, so if a relation is symmetric, then if you have xy, then you should also have yx, and this should hold for any pair of xy's. Okay, and how do you spot symmetry in a relation? When you look at the D graph, you have to have, if you have one way edge from one vertex to the other, you have to also have it the other way. Okay, so if you like have from this element to this element, you have a relation. For the relation to be symmetric, you should also have the other way. And this should hold for all possible pairs. So if you do not have relations both sides, that is also okay. But if you have like this or this, then your relation is not symmetric. And when you look at the 0-1 matrix, this is simple. The matrix itself must be symmetric. Okay, remember this relation is on set A, so it's a square matrix. It's from set A to set A, so the number of rows and columns are the same. And for a square matrix, how do you spot symmetry? Take the transpose, the matrix should stay the same. The third is anti-symmetry. Now, this is important. This is not the opposite of symmetry. Okay, we'll see some examples. It doesn't mean that when a relation is not symmetric, it's anti-symmetric. That's not it. Or it's not the other way around. When a relation is anti-symmetric, it doesn't mean, it may not be the case that it's symmetric. Okay, so let's look at the definition. So what is anti-symmetric relation? For all xy in A, if x is related to y and y is related to x at the same time, this should imply x is equal to y. So what does this mean? If you have x and y here, if you have something like this can only happen if you have this loop and x and y are the same element. So that means if you have two different elements, x and y, you can either have this or this or this without any relation. Now this you cannot have, okay? This is what we call anti-symmetry. This is the definition. And as I said, symmetry and anti-symmetry are not complete opposites. Now, how do you spot anti-symmetry? Of course, when you look at the D graph, no edge except loops should have its opposite in D graph like this one. And when you look at the 0-1 matrix, it's a square matrix. This is the main diagonal. You look at symmetric positions. You can have 0, 0. You can have 0, 1. You can have 1, 0. You cannot have 1, 1. If you have that at any position, then it's not anti-symmetric. And finally, the fourth property is transitiveness. A relation R on set A is transitive if for all x, y, z in set A, if x, y is related, if y, z is related together, this should imply x, z is also related. Now, for instance, x, y is related. This means xy is in R and yz is in R. This means you have z here. In this case, if you have them both, then for a transitive relation, you should have xz also. Okay, if you do not have it, it's not transitive. Now, spotting transitiveness is not that easy like the others. For small graphs or small dielectric graphs, maybe you can check it by hand, by close inspection. But as the relation grows, if the set A is a large set, it becomes much more trickier. Therefore, we are going to define some other concepts to test for transitiveness. Okay, here's an example. The relation divides. So you remember this notation, for instance, 3 divides 6, 1 divides 7, 5 divides 15, or 4 doesn't divide 17, etc. This is the notation we use for divides. And this actually represents a relation. 3 and 6 are related, 1 and 7 are related, 5 and 15 are related through this relation, the divides relation, but 4 and 17 are not related. Now, this relation is reflexive because every number divides itself. Is it symmetric? It's not symmetric. Why? Because, for instance, 2 divides 4, but it doesn't go the other way. 4 doesn't divide 2. Okay, so it's not symmetric. And is it anti-symmetric? Is it the case that when x divides y and y divides x, then x equals y? Yes, because if two numbers x and y divide each other, it can only happen when the numbers are like actually equal. Okay, so it's anti-symmetric. Then finally, is it transitive? Yes, because if x divides y and at the same time y divides z, it should be the case that x also divides z. It's not that difficult to show this. Therefore, the divides relation is transitive. Okay, more examples. And we have D graphs and the 0-1 matrix representations given here. And the first one, in fact, is the less than relation on the set 0, 1, 2. 0 is related to 1, 1 is related to 2, and 0 is also related to 2. And all elements are related to themselves. So it's less than or equal to relation. And this is the D graph representation, and this is the 0-1 matrix. It's upper triangular. And clearly it's reflexive because, well, I see all the loops at all the vertices, and also the main diagonal is all ones. It's not symmetric because the matrix is not symmetric. And it is anti-symmetric because I don't see any 1-1 pairs except for the main diagonal. And it is transitive. How do I see this? I cannot really see this from this matrix. But if you inspect it from the D graph, you can spot that it is transitive. But as I said, we will describe a method to test for transitiveness. The second one, the D graph is given here and the matrix is given here. 0 is related to itself, but 1 and 2 are not related to themselves, so it's not reflexive. Is it symmetric? Yes, the matrix is symmetric when you look at it on the main diagonal. Is it anti-symmetric? No, because we have 1-1 pairs here. Therefore, it's symmetric but not anti-symmetric. And it's also not transitive. Why? Because you have 1, 0 and you have 0, 2, but you do not have 1, 2, so it's not transitive. One counterexample is sufficient. And let's look at the third one. 0 is related to itself, 1 is related to itself, 2 is related to itself, and that's it. So the 0-1 matrix is the identity matrix, and it's clearly reflexive. All elements are related to themselves. It's clearly symmetric. The matrix is symmetric. And it's also anti-symmetric because I do not have any 1-1 pairs. And it's also transitive because it satisfies the definition. I mean, I don't have any two-step paths, let's say, but doesn't violate the definition. So this relation here, as you see, it's reflexive, it's symmetric, it's anti-symmetric, it's transitive, has all four properties. You see, it's both symmetric and also at the same time it's anti-symmetric, right? So since it can have both these properties, this means symmetry and anti-symmetry are not complete opposites. They are slightly different. They are related, a little bit close, but they are not complete opposites.